So originally our school from the very beginning are totally in Russian. But when we have foreign guests or non-Russian speaker, certainly we welcome them to speak English. And Ananya Pal is a postdoc at our lab in High School of Economics laboratory. So Ananya, please.
Okay. Thank you, sir, for the introduction. So today our topic of discussion is Zariski Cancellation Problem and some counterexamples in positive characteristic. So let us begin with some notations. Now for K will always denote a field, okay, and P will denote the characteristic of that field K. K bar will denote the algebraic closure of K. And next, M will always denote an arbitrary positive integer. And next, for any ring R, this symbol R to the power third bracket M will denote polynomial ring in M indeterminants over R. Okay. Now let me clarify the definition of ring. Throughout in this talk, ring will mean associative commutative ring with unity, and K algebra will mean ring, that is associative commutative ring with unity, which is also a vector space over K. Next comes the definition of domain. Let us recall that also. It means it is a non-zero ring, that is associative commutative with 1 and which has no zero divisors. And K domain is simple. It is K algebra plus domain in the above sense. So now let us move on to contents. First we will see what is the Zariski cancellation problem. Next we will see asanomasi. It is actually the first counterexample to the Zariski cancellation problem in positive characteristic for n equal to 3. Next we will see generalized asanoma domains, which are counterexamples for any in any dimension greater than equal to 3. And lastly we will describe some new family of counterexamples that is non-isomorphic to them. So this is our plan. Let's begin. First is what do we mean by Zariski cancellation problem? Zariski cancellation problem asks us, is the affine space AN over a field K cancellative? That is, if we have an affine variety V such that V and then we add one more affine space, we multiply them and we get the affine space n plus 1. Does it imply that V was originally the affine space n? This is the fundamental question of Zariski cancellation problem, and in terms of rings, it's like we have a domain A, we have added another indeterminate W and we have got a polynomial ring in n plus 1 indeterminants. Now the question is, does it imply that A was a polynomial ring in n determinants to begin with? This is the basic question. Okay. So now the answers. First, for n is equal to 1, the answer was yes. It was proved by Abhyankar, Ikin and Heinzer in 1972. Then for n equal to 2, again the answer was yes, but it was proved in a number of steps. First for characteristic 0, then for perfect field, and at last for any field by this Fujita, Miyanishi, Shugi, Russell and Bhatwadekkar and Gupta. Now for n equal to 3 and characteristic 0. The question is still open. We don't know the answer to this question. Either it is true or false, we don't know. But for n greater than equal to 3 and the characteristic of the field positive, we know that the answer is no. That is, we have some counterexamples and they were first provided by Neena Gupta in 2014. And they were asanomas threefold and generalized asanoma domains. Okay. So next, let us define something called exponential map. This was very instrumental in proving that the spaces were not affine spaces. So first, over an algebraically closed field K, exponential map on a K domain is essentially G action on the set of maximal ideals of A. Now let us recall the definition of exponential map. For defining exponential map, we should have first a K algebra homomorphism. Phi or phi of u is an indeterminate over here, which is from A to A of u, okay, and satisfying these two properties. That if I go from A to A of u with the help of phi of u and then go from A of u to A with the help of 0, I will get back identity. And then it's like if I go from A to A of u with the help of phi of u and then go from A of u to A of ub with the help of phi of v, V keeping U fixed, I will get phi of U plus V map. Okay, if these two properties are satisfied by any k-algebra homomorphism from A to A of U, we call them exponential map on A. And then comes the ring of invariance. It's simple, all those elements inside A which are not moved by phi. And there is another terminology called non-trivial exponential map. Everyone has guessed it. It's something that everything is not fixed by phi. Something is there extra. And next come two indeterminants. First one is Duksan indeterminant. It is the smallest subalgebra of A containing kernel or the ring of invariants of all the non-trivial exponential map on it. Okay, and next come something called ML of A, Makal-Limanov invariant. It is the intersection of all the ring of invariance of the exponential maps on A. And there is another thing that over a field of characteristic 0, exponential maps are nothing but LNDs, locally nilpotent derivations on A. So now let us prove a quick lemma on this thing. It says that if m is greater than equal to 2, then decay of this polynomial ring in M invariant is actually itself and ML is itself. It's very easy, we will just go through the proof. We will define exponential maps, phi i's, where I varies from 1 to up to m by this. That is, we will take xi, same I, to xi plus u, and we will keep all the other xj's fixed. Then it can be shown that the ring of invariant of this phi I is the polynomial ring with xi missing. And hence it is easy to see that Duksan invariant is lying inside this. Hence Duksan invariant is the whole ring. And again Makal-Limanov invariant is lying inside this, and this intersection is xi missing here. So it will be k again. So we are done. Now let us introduce something called Asanoma's threefold. So we are now in a field of positive characteristic. P is the characteristic of the field. And we are defining a domain of this form. K, x, y, z by the relation x to the power my plus z to the power p to the power e plus t to the power sp, where m, e and s are all greater than or equal to 1, but p to the power e does not divide sp and sp does not divide p to the power e. This is the formula. This is called Asanoma's threefold. It was shown by Asanoma himself that if small x is the image of capital X in A, then A satisfies the following two properties. That is, A is something called a stably polynomial ring. That is, if we add one indeterminant, we will get K4. But A is not isomorphic to Kx2 as Kx rings. This was shown.
What is P to the power 1?
Sorry?
What is P to the power 1?
I have just added one indeterminant.
Polynomials in non-trivial.
So, and the question was, it is known as Asanoma's dilemma, is A a polynomial ring in three indeterminants? And the answer was given by Neena Gupta in 2014. It says that decay of A is actually kxyz, where xyz are the images of xyz inside A. So the decay is not equal to A. Hence, we can conclude that A was not a polynomial ring by lemma 1. We just proved that if A, for polynomial rings, decay are itself, but here it is not the whole of A. So the A can never be a polynomial ring. So next, this is Asanoma's threefold, we all know this, but here a certain thing was noticed, that this thing GZT, I have written it down again, is actually an example of something called a Segre-Nagata non-trivial line, a much bigger class of something. And what do I mean by non-trivial line? Non-trivial line, I mean that it is a line that is KZT by G is K1, but G is not a coordinate here. And then Russell asks this question, that replace this thing by something much more general, that is by a non-trivial line. Then is K isomorphic to the polynomial ring in three variables? The answer was given again by Neena Gupta ma'am, and the answer, she gave a little bit more generalized ring. She considered fxzt where f0zt is a non-trivial line but m is greater than 1. And there she proved that yes, again A is a stably polynomial ring, actually a one stably polynomial ring, and A is not an affine space. So again we have got counterexamples to the Zariski cancellation problem. Okay, next let us go to the n greater than equal to 3 examples. They are called generalized.
By non-trivial line you mean some variety.
So non-trivial line means this.
Okay.
This is the definition of non-trivial line.
Thank you. I'm sorry.
So now comes generalized acinoma domain. They are defined like this. That is, now instead of x, I have plugged in x1 to the power r1 or up to xm to the power rm, where ri's are greater than equal to 2. Ri equal to 1, we don't know the answer. And we have also assumed that if I put 0 in all these xi's here, I will get something which is non-zero. And then it was proved that again, if the characteristic of the field is greater than 0 and f of zt is a non-trivial line, then A satisfies the following two conditions. A is again a stably polynomial ring and A is not a polynomial ring. Hence, we get counterexamples to the Zariski cancellation problem. So now we have counterexamples to the Zariski cancellation problem in every dimension greater than equal to 3. So now let us, this is the notation I am going to use. For any G, one dimensional, G is a polynomial in one indeterminate, and f inside k of zt, we are defining this. A g1 up to gm f is defined to be this, k x1 x2 xm yz divided by this relation, linear relation. I will recall it, so we already know this. Now we consider this collection, characteristic of the field greater than 0, and we are considering this collection, that we have replaced g1, g2, gm by something specific, monomials, x1 to the power r1 up to xm to the power rn, where ri's are again strictly greater than 1 and f is a non-trivial line. Then let us see an example of this, element here. It is something I can plug in ri's to be 3 all over, and f is a non-trivial line. We already know an example of a non-trivial line. I have just put here s equal to 2 and the characteristic is taken to be p greater than 2 in order to satisfy this condition that p to the power e does not divide sp and sp does not divide p to the power e. So this is an element inside omega 1, the collection that we are going to talk about. And it was proved by Ghosh Gupta in 2023 that if I take two elements from this omega 1 collection, then they are isomorphic if and only if this ri's and si's are equal up to permutation. That is, otherwise if they differ by only if they differ by a permutation they are isomorphic, otherwise the rings are non-isomorphic. So now we have many examples of Zariski cancellation problem in any dimension greater than equal to 3. Now we have something called epimorphism problem and Abhyankar-Sathe conjecture. Let us recall it very quickly. Epimorphism problem is another problem in affine algebraic geometry. It asks us if H is a polynomial in n determinant and H satisfies something. This is called H is a hyperplane. That is, the ring kx1 x2 xn by H is actually a polynomial ring in n minus one indeterminate. Does it imply that H is a coordinate in x1, x2, xn? Now first, for n greater than equal to 2 and the characteristic of the field greater than 0, the answer is no. We have already seen such examples. They are Segre-Nagata non-trivial lines. But for n equal to 2 and the characteristic of the field to be 0, Abhyankar, Moe and Suzuki proved that yes, epimorphism problem is true. That is, in characteristic 0, there is no non-trivial line. If something is a line, it is a coordinate. So, but for n greater than equal to 3, characteristic of the field to be 0, the question is open. So, and there is a related Abhyankar-Sathe conjecture which says that over a field of characteristic 0, this thing is true. That is the main claim of the conjecture, but now they are over a field of characteristic 0. But partial results were obtained even in arbitrary characteristic for specific forms of H. So we made a study of one of those forms, and let me introduce, before introducing that, let me introduce something called R divisible polynomials. They are a bit technical, so let me quickly go through it. It says that you take m tuple of vectors from z to the power m strictly greater than 0, and you take a polynomial alpha from m polynomial ring. Then we call alpha to be R divisible if there exists a system of coordinates inside this polynomial ring such that first instant x1 to the power r1 will come out. That is, this polynomial is divided by x1 to the power r1 and the remaining is not divided by x1. Then you put x1 equal to 0 here, okay, and then x2 will come out. So in this way we will go on. So what do I mean by this? I mean by this, if m is equal to 2, then alpha is r1 r2 divisible in the system of coordinates x1 x2 if alpha is of this form. At first x1 will come out, then I will put x1 equal to 0, that is, I will take it out, and then x2 will come out.
So by system of coordinates, which change of variable do you allow? Any automorphism polynomial ring or
Yes.
just linear one?
Yes, any change of variable.
Any automorphism polynomial ring?
Yes. And so let us quickly go through an example. Here the coordinate system is very important. Okay, that is the proof, because here I am claiming that this is 2, 3 divisible in x2, x1, not in x1, x2. And why is that? Because here it's clear that x2 is sitting here. So x2 is already sitting here. So I am going to just write it in a correct form. It will be like this. Then we will take out x2 from this, and from whichever monomial I can, I have taken x2 out, and then the remaining was is just x1 cube. So it's x1 cube plus 1. So it is of this form. So it is 2, 3 divisible. 2 is here and 3 is here. Okay. So now the theorem in connection to epimorphism that we were considering and which led to this new counterexamples to the Zariski cancellation problem. We will consider here field of any characteristic, okay, here any field. Then we will consider this polynomial ring in m plus 3 indeterminates. Then we will consider m tuple of vectors, each one strictly greater than 1. And H is this equation, that is alpha x1 x2 xm y minus small f zt and then minus h, which is a polynomial in x1 x2 xm z and t, such that this small f is not equal to 0. And we have another condition, every prime divisor of alpha divides h. Okay, then we consider this ring B by H to be A. And then we again put some more conditions that alpha is R divisible. We just now discussed the definition of R divisibility, that alpha is R divisible in the system of coordinates which look like this, and this lambdas are elements of K bar, that is from algebraic closure, such that if I consider this field generated by lambda 1 up to lambda m, this is separable over K. So a lot of conditions, but with the help of these conditions we were able to prove that the following statements are equivalent. And here is 5, we have 8 more, I have just written 5. So it's first it shows that H is a coordinate in this polynomial ring of m plus 3 indeterminates if and only if A is a polynomial ring, if and only if f is a coordinate, small f, and if and only if A is a stably polynomial ring in any L, but with ML of A has to be K, that is trivial, or it is a stably polynomial ring but with dk trivial, that is dk of A is equal to A. So with the help of this, what is our okay, let us discuss some examples, because this R divisibility is not a very good notion. It says that the above family includes the following hypersurfaces. First, this, again this, that is I can replace this R by some this kind of polynomials which are separate and such that every prime divisor of this divides H, and this each AI has a separable multiple root. and again this is something non-trivial, this is also included. So these are the examples. Now let us quickly jump to the conclusion, consequences. Remember this, we have already defined this. So from this theorem A, if we take the characteristic of the field to be positive and F to be a non-trivial line, this is the definition of non-trivial line, then by theorem A, the equivalence of 2 and 3 guarantees us that this kind of A with this kind of F is not a polynomial ring. Okay. And next consequences, we will recall a theorem. It is a theorem by Neena Gupta ma'am. It says that if R is a domain and if I take some elements from R and G is an element inside RZT, such that this condition holds, that is I divide by, this is product, okay, this is product of pi i's comma G, which is isomorphic to R by this ideal product of pi i's to the power 1, that is polynomial ring in one variable, and D is this ring, that is R y z t by a linear relation. Here all the Ri's are greater than equal to 1, then D of 1 is actually R of 3, and this is R isomorphism. And from this theorem, we can conclude that if F is a line, then this is a stably polynomial ring. So combining the previous one and now, when the characteristic of the field is greater than 0, F is a non-trivial line in KZT, then by theorem 1 and theorem 6, we get that this AGI is F with the condition that F is a non-trivial line, and GI has multiple root, one multiple root at least, is a counterexample to the Zariski cancellation problem. So these are the new examples, and we will prove that there is something with a non-isomorphic to the previous one. So again recall this symbol. Now we are going to define the characteristic of the, we are going to define a collection. Characteristic of the field is greater than 0, this is omega 2, that is everything here, but now we are taking GIs as only multiple roots. Earlier it was one multiple root, now it's every root is a multiple root. Then we were able to show that if I take two elements from this omega 2 and FZT is not linear with respect to any system of coordinates in KZT, this here the collection of non-trivial lines get included, so it's a little bit general. Then we were able to show that if we have an isomorphism between these two elements, then the GIs and the HL should have equal number of roots with equal multiplicity. Moreover, one GI will exactly go to another HL. I cannot break it. So this will give us the non-isomorphisms of the omega 3 that we are going to define. So this is an isomorphism result. Okay, now again now we are going to define something called omega 3. Again the characteristic of the field is greater than 0, omega 3 is these things, but now we have the GIs as only multiple root and some GI has at least two distinct roots, and F is a non-trivial line. With all these conditions, let us see an example. What do I mean by this? Again we are in a field of characteristics strictly greater than 2 and we are defining this A2. Now we have added x13, x1 minus 1 cube, xm cube, xm minus 1 cube, and these are all multiple roots, so no problem, and this is the example of a non-trivial line. This is an example of an element inside omega 3. So let us delete this example and write the conclusion. That let F be a field of positive characteristic, then there exists an infinite family of pairwise non-isomorphic domains in omega 3, because in omega 3 we have taken some GI should at least have two distinct roots. So the previous theorem 7 guarantees that they can never be isomorphic to the generalized Asanoma domains, and they were already counterexamples. So now we have infinite family of pairwise non-isomorphic counterexamples in omega 3 for every dimension greater than equal to 3, which are non-isomorphic to the members of omega 1. That is the previous known examples, counterexamples. In fact, we have defined here, just now we have defined something called A2, and previously we had something called A1 from omega 1, and they are also non-isomorphic. So I think I am done. These are the references. and these are the survey articles, and here are some other references that I have used in this talk. Thank you for your time and attention.
Okay, any questions, comments?
Maybe, do you know some candidates for to be counterexamples to homomorphism problem and Zariski Cancellation Problem in zero characteristic? I know the example due to Descartes and Data.
Yes.
Do you know some other candidates?
So one candidate is this Chorus-Russell threefold.
Yes. Okay, maybe some more.
No, sir, I don't think these two are the only possible counterexamples I also know of. I also don't know of any
For
other.
this, but the Data counterexample, it's proven that the factor is K3.
Oh no, sir, I'm sorry. That is a counterexample to something called, possible counterexample to something called affine fibration problem. The Bhattwar-Data example that you were talking about. And Chorus-Russell threefold is a possible counterexample in characteristic 0 to the Zariski cancellation problem.
So in that particular data, if it is proven that f is not a coordinate, then Zariski cancellation.
No, sir, there is a problem. Actually, let me go back. The problem is that we have assumed that f of 0, 0, we have an assumption which fails in that example. That's why we cannot apply, so this condition. It looks like a very innocent condition. We have assumed that f, when I put x1, x2, xm to be 0, then it becomes non-zero. But this Bhattwar-Data example that you are talking about, it fails this. It becomes 0. So we cannot apply our theory there.
Okay, then discuss.
Yes.
Okay, yes. Ananya, and you already have some experience, good experience working on this problem. What is your feeling? Will it be true, Zariski cancellation problem with zero characters?
Sir, I don't.
What should we do? We should construct counterexample or to prove that this is correct statement?
So I think the Zariski cancellation problem will be true at least for n equal to 3. Because the people have tried so much with this counterexample, and each property has almost shown that it is a stably polynomial. They cannot differentiate. So maybe it is true. That's why they cannot do it.
So that the answer is false. If you would like to try to prove that it is true, it is very difficult. But if you can give a counterexample, you can just write something, and maybe it's easy to prove that this is counterexample. So this is the reason that most people try to give a counterexample.
But it has some of the wrong proofs also. Some people tried to give proofs of that n equal to 3, the Zariski cancellation problem is true. But after some steps, there were some faults found, and then the proofs were discarded. So
and what is a possible approach to prove positive results that Zariski cancellation problem holds for zero characteristic? Say some characterization of affine spaces.
Yes. So we have to have a very good characterization of affine 3 space. We have a very good characterization of affine 2 spaces. That is UFD, LND, and no non-trivial units. It is an affine 2 space. But in affine 3 space, we don't have any such kind of good characterizations. So maybe one of the ways is to find the characterization of A3.
Okay. If no more questions, then let us thank the speaker.